Dear participants, welcome back. So let's start our first technical session. Session chair for the session is Professor Dr. Habibur Rahman. Our first speaker is Engineer Eric Lesleighter. He will be presenting online, and the title of his talk is Challenges in Design of Hydraulic Structures. Engineer Eric Lesleighter has more than 40 years of professional experience in different aspects of water-related projects, including design and review of hydropower projects, geomorphology of rivers and sediment transport, flow-induced vibrations, turbulence, cavitation, and air entrainment in hydraulic structures. During his professional career, he has completed a large number of projects in Australia and 20 other countries of the world. So let's proceed with the presentation. Engineer Eric, can you hear me? Engineer Eric, please unmute me. Engineer Eric, can you hear me?
I can hear you, yes. Can you hear me?
All right. So the floor is yours. Kindly proceed with your presentation.
Okay, we'll give it a go. I have to open the PowerPoint. You can hear that?
Yes, we can hear you. You can start. You just say next and we'll change the slide.
Okay, we'll give that a go.
All right. Yes, please go ahead.
Well, the first slide you see is the title slide.
Right.
Yeah. Next. So by doing this, we will all of my selections of 1, 2, 3, and so on each slide, you will not see, huh?
Whenever you'll say next,
you'll see every slide in its totality. You will not see it as I click the mouse.
Yes, we cannot see your screen.
No, I know, but you're going to show the PowerPoint that I sent as a PDF, I gather.
Yes.
Which will mean that the selection button that I use to show a PowerPoint, you will not have. Is that right?
Yes, we cannot see the PowerPoint. We just have PDF.
That's going to mess it all up pretty bad.
Oh.
I think there should be a way I can hit the PowerPoint up, I would have thought, surely.
If you like, you can quickly send the
PDF. It's just going to be a disaster.
If you like, you can quickly share the PowerPoint with us and we'll run it in PowerPoint format. Is it possible for you?
Well, I can do that. It's 22 megabytes. I'll try to. Would you like me to do that? You give me an email that you want me to send that to?
Just send it on the same email address, Shahid. Send it to Mr. Shahid.
Okay.
Okay, Mr. Eric, I think just to save time, we can go with the PDF because we are running a bit late in our schedule. So.
Yeah.
All right.
Well,
let's run the presentation.
If you have to do it that way, let's do it that way. Then, if you want to do it that way. Okay.
All right. So I'm going to show the presentation.
You got the first slide up now?
Just a moment. All right. So now we have your slides on the screen. Please go ahead.
First slide is up. Title slide. Yeah.
Yeah.
Okay. The next one, I was clicking through why this introduction. I mentioned here, I was impressed by the acknowledgement of the prophet in the way you introduced the seminar. And I just wanted to mention where I come from. If I can seek your indulgence in doing that, this is my life as a Christian. So we're just sharing our faith. Right? Now the outlet works. I'm going to be looking at outlet works and bottom outlets. Initially, I want to stress that largely I'm dealing with transients, not the static type conditions that we tend to find a little bit easier, but rather transients. So I'm on a slide now which starts with my content. Okay.
Yes, please.
Okay, so I'm going through the subject categories. There's turbulence, structure fluid interaction, flow induced vibration, oscillating detachment, cavitation and air, sediment laden flows in outlets, and energy dissipation. These are the subject headings I'm just going to use as I continue. Next slide. Turbulence. So here we're starting off by defining the difference between laminar and turbulent flow, the Reynolds number being a number that we use to delineate the difference between those two types of flow, where V a velocity, L a length, and nu the kinematic viscosity. I just make the point there that the viscosity is important in energy dissipation and in transients. Large-scale turbulence, as distinct from small-scale turbulence, large-scale turbulence or macro-scale, is dependent upon the Froude number of the flow. Small-scale turbulence, the microscale, is key to the energy dissipation process. So it is when heat is produced, when energy is dissipated. So this is the same slide again, but I've got some red on it. So this is relevant to increase the viscosity because small-scale turbulence is governed by viscosity. Going to the next slide, I will move the beyond the little statement at the top. I'm looking at transient behavior in fluids. The degree and the location of turbulence is relevant, but turbulent motion is not strictly random, because often in turbulent flow, there is a lot of frequencies which are important for our structure. Solid fluid interaction will likely relate to the intensity of turbulence. The energy spectrum has certain frequencies which are important in the design of hydraulic structures. In the hydrodynamic fields, there are frequencies of interest in the design of gates, outlets, trash racks, and sender members. Frequencies less than about 30 hertz are important, usually in the design of hydraulic structures. The Tacoma-Narrows Bridge, it failed in 1940 due to a relatively low-speed wind blowing sideways. So the designers didn't really appreciate the fact that vortices are shed by flow passing over a structure such as that. It vibrated severely and dropped into the bay. So the failure was put down to the combination of vortex shedding and low torsional rigidity. Some time ago, I'll tell you about a project I was involved in where we were looking at the pitot tubes which are installed on the inside of pressure pipelines leading to a power station. Sorry, I've jumped ahead beyond the drawing. But we have vortex shedding from this pitot tube. In looking at the flow separation and vortex shedding from a structure, we have the Strel number is normally an important number to use. It's related both to the velocity and the width of the structure. Typically, it's about a value of about 0.2, but often it changes a little bit less than that and sometimes more. Vortex shedding produces a fluctuating lift force, which is a sideways fluctuating force, and a fluctuating drag force in the direction of flow. And if the vortex shedding frequency tends to equate to the natural frequency of vibration, you can have what's called lock-in and therefore a vibration of the structure. In this case, we have these Kármán vortices shed from the pitot tube. In this case, we had velocities of 15 meters per second, a width of the pitot tube of 0.19, and a Strel number of that. The frequencies of interest because it has a shedding frequency of 150 hertz, and in water, the natural frequency was 183, which means it was possible to lock in, and it failed. And those pitot tubes were found having passed through the turbine into the draft tube. They broke away. This shows vortex shedding at the bottom of a gate lip. More about that a little later. The Reynolds number effects on flow passing a structure like a trash rack bar. There are drag coefficients on the left, lift coefficients also on the left, and then Strauss numbers on the right. But it's possible to have these very well-defined frequencies of vibration which could cause trash racks to fail. And for this causes this flow structure interaction, vibration of the structure. In trash racks, you have to design bars such as that so that they don't have this high excessive transient loads using lower velocities. A few situations where there were some problems in the Raccoon Mountain in the USA pump storage project, they lost all their trash racks because they vibrated because of this lock-in between the vortex shedding and the natural frequency of vibration. In one of our projects in Australia, the T3 inlet outlet structure, we had a 5.5 metre diameter jet expanding through the trash racks that in the pumping mode at 3.6 metres per second. That was an issue which we had to design for. Another project here, the Tamsalk project, which had one failure. Draft tube trash racks were found in the tailways. Fatigue cracks were found in the vertical bars, so it's a vibration problem. And often in our design of hydraulic structures, unless you know a bit about flow-induced vibration, you can come to some sort of grief. So there's clear evidence of the forcing frequencies equating to the natural frequency. In trash racks design, therefore, you have to look at the possibility of flow setting up this vibration, flow-induced vibration. There are many such cases. I'll jump to the slide which starts with oscillating flow detachment. Gates, where structural vibration is very important. It can be a small scale instability which can send gates into excessive motion. In this case here, we have one in Australia, excuse me, the Wivenhoe Sprit-Yard control structure. If you're taking notes, there is a paper on that one, which I've included the reference there. We modelled that at a scale of 1 to 24. Studies showed a marked effect of gate bottom shape on downpour forces and on transient shifting of the flow separation. In this case, we tested, you have the drawings there, you see an original and a modification of the bottom of the gate. And on the right-hand side, the downpour force on the gate was very much dependent upon the shape of the bottom of the gate. So modifications were used then to avoid the excessive downpour forces. These were modelled hydraulically. That is, we had the scaling of the gate mass, the gate suspension, and the hoist cylinder. You're saying something? Sorry. Okay, the original gate had unstable separation of the gate bottom. There was the self-exciting vibration which could occur. We wanted to avoid that. This is a mechanism that has been described by others, such as Coltman in 1976. Considering the natural frequency, the turbulence-induced force, maximum fluctuating force amplitude is almost the same as the downpour force, so we had to have major modifications to that gate shape on the bottom of this Wivenhoe structure in Australia. Moving to this slide, which has Coltman at the top. Coltman did a lot of experimentation and also has published well on self-induced structural vibrations. Petrikat Stuttgart also has a number of papers. These are references worth studying if anybody wants to get into the flow-induced vibration area, which is important for the hydraulic structure design, then these are authors worth checking out. Naudascher in Karlsruhe in Germany also. Looking at categories of fluid dynamic, fluid resonant, fluid static excitation. The fluid dynamic is just the structure vibration alone. The fluid resonant situation is where the flow body itself can set up a resonance within the water, which also then leads on to the fluctuation of the structure. And then the function of the structural resonator is when the thing vibrates like a tuning fork. Resonance and outlet structures. One example is this job in Yugoslavia. Outlets exiting in the hydraulic jump, and so you have a conduit passing through the dam, hydraulic jump dissipator, and there was a feedback situation with turbulence in the stilling basin was fed back through the opening, and it caused very large fluctuations in the base of that dam and in through the conduit. In this case, a project in Brazil that I was working on, we have 8 diversion gates modeled in Germany and in Japan. And the purpose of this was to look at the possible hydraulic force which would come into play when these gates were being lowered during the closure of the diversion. Again, original gate and changes made to the base of the gate. And looking here, we have the downpour forces. Depending on the gate opening here, if you have a 4/8 gate opening, that's 50%, you get a big downpour force, much less when it is to the right or to the left. Bottom profile was varied to achieve a much lower downpour force. This is some of the variations from 110 tons, 104, 93, and 84 tons, varying depending on the base, the bottom of the gate. Gate vibration was a consideration. It came down to ensuring that the gate servo motors themselves provided good operation of the gates. In Australia, the Dartmouth low-level outlet works. The design of these gates under heads up to 170 metres. As you can imagine, cavitation was a major issue. The gate mass was considerable, so we could not have a knife edge at the bottom of the gate, so we have an 80mm wide gate lip so that the gate itself and its great mass would be seated on a stainless steel base a pad at the bottom without cutting into it. So there's a concern that there's a shifting detachment of the flow separation under a gate like this could cause separation, or which would cause flow-induced vibration. But the major issue in this project was cavitation. In this case, we have 2 conduits discharging into a 10.75 metre diameter expansion chamber. Cavitation, when flow bends over a shape, streamlines don't follow the shape. They tend to go together or they separate. So there's rather an increase or a decrease in the apparent depth of flow. And you can get vapor pressures caused if the pressure drops low enough, and you have what's called vaporous cavitation. Cavitation bubble collapse is a violent process that generates these highly localized, large amplitude shock waves and microjets.
Eric, sorry to interrupt.
Yes.
Can you please specify which slide exactly you are on? Is it the right slide that we are showing?
Oh, okay. The one I'm on now, it starts with cavitation and cavitation index based on Dartmouth.
Can you please give me the slide number?
I haven't got them numbered.
Okay, just hold on. Let me show you some of the slides.
So let's do a bit of a search. We might be able to, if I go backwards, the one before it shows 2 drawings of an outlet works. In the heading is cavitation index based on data.
Okay.
You got it?
Just a moment. Okay.
This one shows the structure in profile and in plan, 2 converging conduits.
Okay.
The bottom outlet works at Dartmouth has a cavitation number defined there based on the upstream and downstream head and the vapor pressure.
Next is this one.
This one, the side I have now has a little red sigma symbol. For a general
Okay.
representation of the system, we use sigma. But flow
This
through a
one.
gated outlet has many cavitation numbers. That's the text. You not see that one?
Next. Red signal. Next take करें. ये वाले. Okay.
Got it?
One. Okay.
A typical system cavitation number for Dartmouth was 0.1 to 0.3, depended on the head on the structure. Downstream orifice was provided to increase the submergence and therefore to increase the cavitation number. This is showing a trail of vortices. If you have the picture, in a bluey color picture, showing vortices from the base of the gate, which was in the model. I hope you can see that. These are large cavities which, when passed out into the expansion chamber, they collapse. And of course, they collapse in microseconds, which is why cavitation pressures are so very high. This is a picture, I hope you see it, of an expansion chamber, cavitation going into an expansion chamber where all the cavities collapse. Concern about a shifting detachment is on the top of this next slide. It was not gate vibration, but the shedding of cavitation vortices, which was important. So, is cavitation a problem? Well, facetiously I say there, well, if you have a material that can withstand implosion pressures of 15,000 atmospheres, there might be no problem. But we do not have those materials. So cavitation was a certainty, but to counter the effects, provision was made for air admission through the gate lips and the 1.5 metre conduits and 25 millimetre thick austenitic stainless steel lining, figuring that the stainless steel would be able to withstand the cavitation collapse pressures. Measurements were made during commissioning. Now this slide, I hope you can see it, it shows downstream orifices and transducer location. It shows 3 blue arrows on the slide.
Yes, we can see that.
Going where we have pressure transducers on the upstream side, and then we have one called TQ22, a transducer, and then there's a plan view at the bottom showing the transducers which we put in place on the side walls. Transducer TQ22 was reproduced very harsh pressures. Here we have some captures of pressures recorded on a digital oscilloscope. If you look at the one on the right, you'll find where we have one pressure spike of up to 1500 megapascals. And I've enlarged that in the time scale on the right. So you can see it's a very rapid down into the microscale range or microsecond range. 1500 megapascals was caused a lot of damage. We set up in the with all this sort of equipment in the valve house. What did we get? Well, if you ever thought that the only type of cavitation damage was pitting, such as you see in this picture, you have to think again, because in this case, under heads of well over 100 meters, the cavitation expressed itself audibly as like heavy bombardment of guns, very heavy artillery, and caused damage to the conduit with dents on the sidewalls with pressures up to 1500 MPa. Here's a few pictures. I hope you can see them showing dents in the sidewall of the stainless steel. Here's another one, 16 millimeter long dent caused by one cavity collapse. Another one here, a series of cavity collapse. And another one here, 14 millimeters is the length of this dent in the stainless steel. I hope you're seeing these pictures. Now I'm going to a slide which starts off sediment effects.
Okay.
Have that one?
Yes, 7 millimeter. We are on slide with 7 millimeter dimension.
Yeah. So cavitation outlets is one thing, but our outlets have to sometimes discharge sediment. One project I was working on was in Sudan, the Rosieres Dam project. In this case, we had 5 conduits, 10.5 meters high, 6 meters wide, each of the 5 radial gates. They were operated each year to discharge sediment for 3 months of each year, discharging sand and gravel and cobbles. Originally, the invert was part of and as part of it was sidewalls were lined with composite style steel, and then later on, because of damage, the repairs in place 36 millimeter thick martensitic stainless steel over the floor. Now this is the project. These are the deep sluices are on the left. 5 of those. Can you see that? A
Yes.
picture of the dam.
We are on the slide with sediment effects.
If you move ahead, you should see a picture of a radial gate.
Okay, now we are on the slide with the picture of spillway, power station, deep sluices.
Yes. If you go to the next one, see a radial gate.
Yeah, now we see the radial gates.
Well, where the men are standing there, or they're standing on the stainless steel lining, it's rather covered with sediment or silt, but a lot of that floor, as you'll see in a little bit moment, I'll show you more. Next slide. This was the original composite, which only had a 3 millimeter stainless steel over mild steel. This is damage right through the 36 millimeter. There's a hole in the stainless steel. The next slide shows a series of damage in the wall, like a waveform type damage in the surface of the stainless steel. This is not cavitation. This is sediment caused this. The bottom of the radio, and you might see a slide now with 2 hands pointing at various features of the cavitation, of the sediment scale damage. See those hands?
Yes.
Good. There's another one there in the bottom of that picture. You can see a hole through the 36 millimeter stainless steel. This is looking across. The next slide is looking across the base of the conduit, the 6 meter wide conduit, and a lot of it is very, very badly damaged from the sediment. This is the side wall. There's also damage on the side wall from sediment impacting the side wall. Concrete was eroded to 150 millimeter depth downstream of the stainless steel lining. So you can see the reinforcing appearance there. Next slide. Next slide shows, talks about the cause of the extensive damage was considered by some to be largely due to cavitation. But no, it was not. It was damage due to the abrasion and erosion by large quantities of large, hard sediment discharged through the structure. The damage by sediment abrasion in stainless steel is interesting because of the fluted patterns. In this, you possibly see a picture now with the turbine runner damage. You get sediment abrasion in a turbine runner in India. Might have to click forward to find that slide, I hope. The turbine runner, a naphtha project.
Do you see the runner?
You got that one?
Yeah. Yes.
Yeah, okay. Moving to the next slide, this is some of the damage to the guide vanes in this turbine installation in this Indian project. Then some of the guide vanes that were repaired on the right-hand picture. The problem of sediment abrasion in hard steels, typical of many projects. The Himalayas being one of the sources of a lot of sediment, as you already know, you gentlemen already know. To illustrate the impact that provision for sediment has on projects, not so much in Australia, but certainly very common in a lot of countries. Reservoir sedimentation means that major dam developments are often threatened within a few decades. Your audience would all know that. Outlet works normally call for steel line conduits, radio gate control, and the bottom statement here, the next photo shows the models tested for the Dama Vashu project in Nandipur. I took a picture of that one, and also the next picture after that one is this project in Nafajakri, where the control structure here was all lined, or the spillway is all lined with steel and steel rails downstream the top. Do you see that one with yellow writing? Nafajakri.
Yeah, steel lining.
Steel lining, yes. Next project, next slide is energy dissipation.
Right.
Pass down to Dartmouth. We had this 10.75 meter diameter expansion chamber, 45 meters long. We had high level outlet works for using cone valves. And for some of this energy dissipation, we have to use the hydraulic jump stilling basin. For a hollow jet valve, there's a special basin. For some jets are discharged into the air. So many of the outlets I've mentioned have been the subject of physical modelling. The Dartmouth low-level outlet works cavitation model equated the cavitation numbers and the Froude numbers simultaneously, and to do that we had to operate a low ambient pressure model. So that was the way we could reproduce those two cavitations at the same time. This one in Brazil, the South Samal diversion gates in Brazil, there remains a major place for the use of physical models, properly scaled. So we have to design our models to have equality between the ratios of importance. I hope you have this slide at the bottom statement here. The gravity is the ratio of the inertia force to the gravitational force. You can digest that one a little later, but that gives us a Froude number. And then at the top here, in the next slide, viscosity is the ratio of the inertia force to the viscous forces, which brings into play the Reynolds number. So you have to have those both into play when we're looking at these conditions of cavitation and energy dissipation, or more strictly as the energy dissipation. There are issues of air entrainment effect. So I'm getting to the end of this discussion of the outlet works. So there are problems, but hey, nothing's perfect. Moving on, challenges. The title of your seminar is Challenges in the Design of Hydraulic Structures. So here are some of the challenges in summary of this part. What we have covered poses these questions. What personnel skills do we have in design teams? This is so very important because in many of the things I've discussed here today, many engineers do not have this experience. You haven't been there, but they're important. How knowledgeable are the design members in the major transient phenomena that exist in major structures? Very important. Do the team leaders know that such expertise is needed? Or do the team leaders take shortcuts and consider specialist expertise is too costly? Could be a bad mistake. Does anyone know about historical failures of structures? On a team, if you've got a design team is working on a major project, it's good to have a good cross-section of experience. Where some of the historical failures, and I've presented just a few of them, it's important to know about them, read about them, and realize that they can happen in yours or my project. Does anyone in the team know about flow-induced vibration, or spectral analysis, or cross-correlation effects, or energy dissipation, or cavitation? Important things to know about. For our major projects, the challenge is to be informed about all of these things and to make the right decisions, to act accordingly. The potential dangers could be cost. Now, I I got some on spillways. Are we running out of time or not? Because we've had some delays and it's been.
Yes, Mr. Ray, you just go on for more about 5 to 10 minutes. All right.
Continue.
Yes. 5
Okay,
minutes
next
more.
slide. Next slide is spillways. Why? There's more than one way to release water from a dam. So if you look at that dam, you can see there's a very large part of the dam that's been blasted out. That's really not a good spillway. We're going to be looking at the approaches, crest, chutes, energy dissipation, chute hydraulics, waves, head losses, cavitation and aeration needs in spillways, pressures, pressure fluctuations, ski jump hydraulics and plunge pools, model testing. Now, I've moved on to the next slide, which shows a picture of a partly constructed crest structure. While the spillway approach, you got that one? Gate details. I'm going to focus, again, as I did for outlets, really on the transient behavior rather than just the ordinary, shall I say, ordinary type of static type conditions of flow. Will it be gated or ungated? That's the next slide. This first part of the slide is gated or ungated. Crest profile, design issues and its effects. The capacity, cavitation, can it start at the crest? Yes, it can. There are plenty of design precedents and manuals for the design of small dams being one of the US Bureau. Here we have just one drawing of a crest design, the Bowman crest design with a radial gate and seating there. Moving on to the next slide, you should see a picture of Hoover Dam side channel spillway with crest gates. I hope you do see that one. Cavitation as for bottom outlets remains an issue for spillways. You can have the vaporous cavitation taking place if we get down to the vapor state in curved flows. So when we get that cavitation in spillways, we could ask, well, is it really a problem? Well, if we have materials that can withstand these very high implosion pressures, there might be no problem. But concrete cannot, and other materials cannot. They have poor resistance to cavitation implosions. Cavitation bubble collapse is a violent process that generates highly localized, large amplitude shock waves and microjets, very small as they collapse. When this collapse occurs close to a solid surface, these intense disturbances generate highly localized surface stresses. You have a picture now, I hope, in the next slide showing the major cavitation damage which occurred in 1983 at the Glen Canyon Dam, Colorado River, USA. Do you have that slide?
Yes.
It shows the huge erosion of concrete, and after the concrete, then the underlying rock was eroded. That was caused by cavitation. It was a very delicate situation they were in there because it looked like the flood was going to go over the top of the dam, but it didn't quite. So repairs for this particular tunnel introduced aeration steps as a means of introducing air into the flow. Next slide, we come to the chute or spillway profiles. In parallel with economies, we want limited height shock waves. We want no nasty effects of cavitation or extreme loads. We want flows which make energy dissipation conveniently handled at the bottom. And the energy unit discharge becomes a factor in the design of a proper hydraulic structure or spillway structure. Here's some examples. This is a project in Iran, 177 meters tall. The structure is on the left. You'll see there are 4 aerators across the structure. On the right, you see the flow discharging here about 20,000 cubic meters per second. Things to note, the 4 aerators and the ducts in the left wall. If you look at the picture on the right, you see the duct openings on the left side wall where they go into the air. See the flow of violence, the pier wakes, the air bulking. The next one is a profile of that particular spillway, the Masjid Solomon spillway. You can see the height. This one is about 177 meters tall dam. So you're looking at the chute and you can see 4 aerators, flow passing down to a hydraulic jump sealing basin at the base. Step spillways, I'm going to show you 2. This is one called Upper Cotter Dam in Australia. Note in this one, the aerator ducts below the aeration step. So there are some ducts here and air passes through the 2 side openings and it comes out through the 5 openings underneath an aeration step. That was one design for a step spillway. Another one here in Malaysia, the Susu Dam. This one is a step spillway. It has the main spillway down on the left of the picture and then the non-overtop section on the right. The bottom side picture shows the actual aeration step is up on the top part of the picture, and then the opening there where we're standing with a horizontal surface, that is actually the opening where the air comes in from the side ducts in underneath the jet. Aerators have been illustrated. Devices have come into their own in the last 50 years. This is on the next slide. Air as an anti-cavitation medium is well proven. If you get concentrations up above 5%, or preferably more, then it's able to control the cavitation collapse pressures. Designs, of course, must allow for bulking. Here's a picture of the Karun 1 dam spillway in Iran. Initially, that spillway had no aerators and it suffered complete loss of the bucket and meters of rock below it. Epoxy repairs were made to the spillway, didn't work. It failed also. Now it has 2 aerators, and you can almost see them in the picture. That dam is now called the Shah Dabasur Dam. Moving on to the next slide, a little light relief. I hope you can see this slide. If the limit of x approaching 8 of 1 over x minus 8 is infinity, what is the limit of x approaching 5 of 1 over x minus 5? And the answer is 5 on its side. That's just for a bit of humour. We're moving on. The cavitation issue is very important, necessary to ensure that its possibilities and the ways to counter its effects are fully dealt with. Pressures. A major issue in sealing basin design is the dynamic pressures on the blocks of that basin floors, the side walls. Transient pressures have to cater for uplift, wall loading, vibration. And then there's always a problem of where to put the drain openings. I'm going to show you here the Kanafuli Dam spillway failed badly. The left picture shows the removal of the slab. Over on the right, you can see a profile showing an
shall
opening.
we go towards the concluding your presentation?
Sorry?
I mean, the time is almost over, and now we'll go towards the conclusions of your talk.
Okay, yes, I'll jump over several slides, then you'll be able to see them yourself. The challenges we have here are similar to what I've said before. Do we have in the design teams, when we design structures which are major like this, then they have to have the right people who know something about transient phenomena. The leaders need to not cut corners, but have the right people on the job. Historical failures, it's important to know about those. Pressure transients, spectral analysis, cross-correlation, energy dissipation, cavitation. For our major projects, the challenge is to be informed and not cut corners. The potential dangers in hydraulic structures if we don't get it right, as a lot of structures have failed. And of course, we've learned a lot from failures. Thank you for the opportunity to address your seminar. I'm sorry it's all been such a mess.
No worries. Thank you. Thank you, Eric.
Thank you very much, Mr. Rick, for your very nice presentation.
You're welcome.
Given the challenges in each case,